In 6.3, we're going to talk about polar coordinates. And just to give you an idea, it's something similar to what we already know within plotting a point, which we use a rectangular coordinate system. The polar coordinates is just a new or a different system that helps us graph things that are not squared, and it works better for circles or curves, if you will. So at the very center of the polar system is what we use to kind of graph our angles in the unit circle. So that's called horizontal array, and so it is called the polar axis. So here is an array. It starts at a point and it goes off with no end, right? It's continuous. So that is the polar axis as we have labeled here. The circle at the very center, or the origin, which we used to refer to in rectangular coordinate system, is called the pole. From there, we're looking here in figure 2 what it would be like to open up an angle in standard position, I think is what we usually call it. And the distance from the pole to the point is going to be known as the radius. How much from the polar axis to that new ray is the angle theta. And so if you kind of see this, there's a new point right here, and that point is going to be defined in terms of the radius and the angle theta. Okay, so r comma theta is what we will know as the polar coordinates for a point. Okay, so if we wanted to plot this point in polar coordinates, I think is what I want to say, it would be something like you have your x comma y coordinate system, right, as before, but this time we want to start with the angle. So where is pi over 3? So because pi over 3 is positive, we locate it by drawing theta equals pi over 3. So pi over 3 is something right here, right? The aperture of the angle. And if you think about it in terms of degrees, this should be 60 degrees, right? And then we want to count the distance. If you were thinking like 1, 2, 3, 4, and those were like little circles. Okay. However much distance away from 0, if you will, in a circular form. So this is kind of how we're building that coordinate grid. Instead of x, y, we're now talking about radius and angle. So if I was to try to plot the point 4 comma pi over 3, but thinking about it in polar coordinates, then this is how it would go, right? I first locate either the angle and just say, okay, this is my angle aperture, and how far away from 0 am I, right? Which is the radius. So this is just kind of like an introduction, one way to plot something like this, we'll get an idea how to do it. Okay, so what can we understand about the sign of the radius and the location, right? So we're given a point and its coordinates are going to be r comma theta, right? It is going to be located r units from the pole or from the origin, right? So the radius tells me how far away from the center it is, either to the left or to the right. And we put it in absolute value bars because the distance away from 0 can be seen as an absolute, right? You're 5 units away to the left, 5 units away to the right. You're still 5 units away, and we add the negative just to tell us which direction. But for now, we're just kind of thinking of it as an absolute value distance. If the radius is greater than 0, meaning it's positive, then the point is going to be on the terminal side, to the right side. Okay, if you remember the unit circle, we had something like this, right? We started with x comma y, and then we said, you know, this is a circle. Oops, terrible finish. And we kind of started saying that this is the terminal side, right? And we define some kind of standard angle, standard measurement of an angle, right? If it opened counterclockwise, right, starting on this positive leg of the x-axis, then that's what we consider the terminal side. Then, if the radius is less than 0, okay, then we say that we're going to draw or start the point on the opposite or to the left, right? So in this distance, right, away from 0 on the left. Now, if the radius or the distance away from 0 is equals to 0 itself, then the point is going to just never leave the center regardless of the angle, right? I can tell you the angle is 150 degrees, but if the radius is 0, then that would be kind of the point where it goes, right? This is just kind of a brief explanation to understand the sign of the radius. So if it's positive, we go to the right, and then we open up to whichever angle. If it's negative, we go to the left, and then open up to whichever angle we're given. But if it's equals to 0, then we stay at the pole or the origin. Here in this graph is kind of what a translation of the XY coordinate system to the polar system looks like. So let's try to draw a couple of the different points here. So first we're going to plot 2, 135 degrees. So if we do it the same way that we started before, so where is 135 degrees? So 135 degrees, it's going to be on the second quadrant, so somewhere over here, right? And it happens to be kind of in the middle between 90 and 180. So I know my angle is going to be, or the point is going to be somewhere here on this line, right? Because that's how much theta is. So this is very hard to draw on, but the idea is that. So, but where is radius 2, right? So this is theta and this is the radius. Well, it happens that this is radius 2 opening to an angle of 135 degrees, right? So I'm going to kind of keep those out and just label this as point A, okay? Then B tells me to the left 3 units. So from the pole, we'll change it to a different color. From the pole to the left, -3, and then open up to angle 3 pi over 2. So notice how I am showing you two different systems to plot a point using rectangular coordinates. Here I looked at the angle and then I adjusted to the radius. Here I am choosing the radius first and then going to the angle. I believe the second way, or the way that I'm graphing point B, is going to be more beneficial. So first find the radius and then open up to the angle in that standard way that we've been doing it. So if the angle is positive, then we open counterclockwise from that point. And if it was negative angle, we would open clockwise. Okay? So 3 pi over 2 is the equivalent to 3/4 of a rotation if we were in the standard, right? 3 pi over 2 is down here, but since we're starting from this point, we go here. 1 pi over 2, 2 pi over 2, and 3 pi over 2. So this is where point B is. Okay, so hopefully that makes some sense. Another way to do it, point B, if you will, is let's start with just thinking, you know, the absolute value of -3 is 3, right? So it's right here. And then I'm going to open up 3 pi over 2. So again, I told you it was 3/4 of a rotation. So 1/4, 2/4, and 3/4, right? But then the negative sign. So that would throw me to the other side, pretty much leaving me there, right? Because of that negative on the radius. So I could look at it as an absolute value number and just carry on with the procedure, but then at the very end I would have to compensate for that negative that was on there. Okay, so hopefully that makes some sense. Let's do point C, and this way, you know, we'll do it whichever way. We'll go with just go on positive. So here's +1, but then I have to go negative pi over 4. So negative pi over 4 means clockwise, and it's in this direction right here. So, but since I did the +1, absolute value of 1, that means I have to go opposite direction and end up right here. Okay, and this is where point C would be. So let's do it a different way so that it makes sense. So it says from the pole go to the left 1 unit, which is right here. Then open up in the negative direction pi over 4. So this way would have been positive. This way right here is negative. right? Because it's clockwise. And a quarter of a rotation, it's right here where the purple dot is. So that's how we would plot the different points. Hopefully that makes sense. So this kind of takes us to the next topic, which is multiple representations of a point. The way I explained it to you on the previous example, by thinking, I can graph the positive of it, but then at the very end, remember to take into account the negative, right? So what I showed you was pretty much an example of the multiple representations that a point can have. So here's the more strict or rigid definition, right? So if a point, if n is an integer, and we're looking at the point r comma theta, it can be expressed as, so r comma theta is the same thing as the given radius, comma, theta plus some multiple of a rotation. So if we go back to this, who's to say that I can go to the right to open up 135 degrees, but then go again another 360 degrees and end up on the same point, right? It doesn't make a difference if I go 3 rotations and end up in the same point. The final position for the point A is going to be the same regardless of how many rotations I do. So keep that in mind. That's what that's saying. Or you could represent the point r comma theta as a negative version of the radius, but with the angle theta plus pi plus a multiple of 2 pi. So what does that mean? Okay, I could have done -2 for point A, and then I go 135 degrees, which would leave me, I believe here. And then if I do the plus pi, which is 180 degrees, and then factor of the rotation, I can go around the circle as many times as I want, and then land on the same point. It doesn't make a difference, because the final solution or the final point lands on the same place as perhaps the original 2, 135 degrees, right? And I can name all those different starting points as different things, but they end up in the same spot. So let's do an example. We want to plot the point 2, pi over 3. Well, let's say that it is plotted. We want to find another representation for the point given this characteristics, right? This is the criteria that we have to meet. So graph this point 2, pi over 3, keeping the radius positive, but the angle has to be between 2 pi and 4 pi. So we'll just say solutions right here underneath. Keeping the radius the same or positive, right? I can't change the radius, otherwise I'm going to end up in some other point. However, we can do pi over 3 plus 2 pi, right? That's going to be the same point. It's just another representation of it. So this becomes 2 comma, and pi over 3, we need to get a common denominator. So this is going to be 6 pi over 3. So 2 comma 7 pi over 3. So this that I have highlighted here is equivalent to the point 2 comma pi over 3, except the angle is now between 2 pi and 4 pi. Okay, cool. Then point B, or question B, we want to rewrite this such that the radius is negative, meaning we're going to have negative 2, but angle theta has to be between 0 and 2 pi. So let's kind of cheat real quick and get an idea as to where my point is. So my point is somewhere over here, right? The original. But this one has to have negative radius. So here's negative 2, and if I open up to pi over 3, I end up right there. Well, how much of a rotation do I need to go from the red point to the black point? So I have the original angle. All I need is an extra half rotation, right? Or pi. So that's going to throw me to the other side and end up on the original point. We'll just call it A. So negative 2, comma, and then this would be pi over 3, and we need a common denominator, so 3 pi over 3. This is going to be negative 2, comma, 4 pi over 3. So notice how we have now two different representations for the original point given, but they are still the same point, right? If we were to graph this, it would land us on the same point. Now we want to keep R positive, but the angle has to be between negative 2 pi and 0, so we want a negative representation. So again, we start with the point given. So what this means is that here in my little example that I go to the right 2 units, but instead of going this direction, I have to go the other direction. Okay, so you can look at it a couple different ways, and so what we're going to do is just take away 2 pi from it. Oops. Okay, why is that going to work? Well, it's pretty much saying we have a full rotation and we're taking away the pi over 3 chunk, but then we just need the negative representation of it. So 2 comma, and then we need common denominators, right? So pi over 3 minus 6 pi over 3, and this is going to give us positive 2 as the radius, and this is negative 5 pi over 3. So if you wanted to go positive on the angle here, well, on the radius, sorry, and then go negative, and then go around and end up right there, that's what we did on the last example. Okay, so actually we have 4 different representations for the same point, right? We have the original here, we have this one where the angle is between 2 pi and 4 pi, then the third representation where the angle is negative, the radius is negative, but the angle is between 0 and 2 pi, and then the last one where the radius is positive but the angle is negative. Okay, Now we want to talk about what are the relationships between polar and rectangular coordinates. So we want to keep in mind some of the definitions that we know, or at least the acronym that helps us remember those definitions. SOHCAHTOA is very helpful. Okay, so given this picture here, and maybe I want to kind of write this in different colors so you know that this is not really the same x as this and the same y, right? This is the x and y axes, but this right here is just some distance x and this some distance y, more specific. Okay, so that's what I mean by that. So let's solve a couple of the definitions that we know. So sine of theta is equals to opposite, which is y, over r, right? But if I want to explicitly have a definition for y, all I have to do is multiply the r to the other side. Okay, so now I have an explicit definition for y, which is what we're looking for. Now I'm going to do the definition of cosine. Cosine is adjacent over hypotenuse, so x over r, right? And then again, if I want a explicit definition for x, all I have to do is multiply the radius, or r, to the other side, and we have this, right? So this is important because now we have a very explicit definition of what y is, what x is, in terms of radius and theta, right? R and theta. Then we want to bring in some of the other old definitions, I guess. Remember Pythagorean theorem in some sense. X squared, or the distance of x squared plus y squared is equals to the same distance as r squared. Okay, and lastly we want to talk about the definition of theta with respect to tangent. So tangent of theta is equals to y over x. Okay, so those are some of the relations that we want to talk about, right? So y can be defined in terms of sine, which we kind of remember from the very beginning when we learned trig definitions. Then x is the same thing as r times cosine. That's very helpful. Okay. Now, why did we need those relations? Well, because we want to be able to convert from polar to rectangulars, and that's the points, really. So let's do this example. We want to find the rectangular coordinates of the point 2, 3 pi over 2. So obviously this is an angle right here, so that's theta, and this is r, right? Hence we're converting from polar, meaning we are given polar, and we want to convert to rectangular. So how do we do it? Well, we want to use those previous definitions that we created up in the previous slide. So y is equals to r sine theta, and x is equals to r cosine theta. Do we know what r and theta are? And the answer is yes. We're explicitly given those values, so we can figure them out. So y is equals to 2 times sine of 3 pi over 2 2 times, what is sine at 3 pi over 2? Sine at 3 pi over 2 is negative 1. So this becomes negative 2. Y has a value of negative 2. Okay. Then we want to find x. X is 2 times cosine evaluated at 3 pi over 2. 2 times, what is cosine at 3 pi over 2? And it happens to be 0, right? So 2 times 0 is 0. Therefore, x equals 0. And let's see. The point 2 comma 3 pi over 2 in polar coordinates is the same thing as the point negative 2 comma 0. Nope, made a mistake. Sorry. 0 comma negative 2, right? So this is r comma theta, and this should be x comma y. Okay, so that is how we would convert from polar to rectangular coordinates. Then we want to do the opposite, right? We want to be given a rectangular point and be able to convert it into a polar coordinate or a polar point. So the first thing that we should do, and the idea is that the radius is going to be positive and the angle theta is going to be between 0 and 2 pi. So given a rectangular point, we're more comfortable working with those type of points. We're going to plot the point x comma y. Then we want to find the value of r, and we use that, well, we find that by using the distance formula, which gives us the radius is equals to the square root of the sum of the x and y squared. Then we're going to find theta by using tangent equals y over x. But then that's not how we really get theta. We have to do tangent inverse in order to explicitly get theta. Let's do an example, and we want to convert the point negative 1 comma square root of 3 into polar coordinates. So what did we say the first thing to do was to actually plot it. So if we plot this point, here's x and here's y, and so if I go negative 1 and then upwards, I don't know, some distance here, something like that. Okay, so you can see that it kind of makes an angle now that I drew it this way, right? So the point itself is in rectangular coordinates, but then when I add the aperture and the terminal angle, then it kind of looks like it could be a polar coordinate. And just know that this distance here is the x equals negative 1, and the upwards is y equals square root of 3, right? Now, what do we do in order to get our r and theta, right? This distance right here is the radius. So remember, the radius is equals to x squared plus y squared. Well, negative 1 squared plus square root of 3 squared, and so negative 1 squared is 1, square root of 3 squared, it's 3, so this is the square root of 4, and we get 2. So the radius is equals to 2. Perfect. Then we want to find theta, and we do that by setting up tangent of theta is equals to y over x, and tangent theta is equals to the square root of 3 over negative 1, so that tells me tangent is equals to negative 3, and then if I do I guess several ways we can do it here. You could do tangent inverse, or you can just do like reference angles, and remember that, so these two are kind of similar to each other, and so we know that tangent at pi over 3 is equals to square root of 3, but because theta is in the second quadrant, then we can do this business with pi minus this pi over 3, right? So that's one way to figure out the angle theta, right? If you don't have a calculator and if you don't remember exactly those values, then at least you want to be comfortable with knowing the first quadrant values, right? That's going to help you do things by hand. If you don't happen to have a quick reference to the unit circle and things like that, then this is going to be very helpful. So when we finish, we figure out that the point negative 1 comma square root of 3 is the same thing, or once it's been converted to polar coordinates, as 2 comma 2 pi over 3, right? This is an xy, but this guy right here is going to be an r theta, right? Now, the next thing that we're going to do is work converting equations, but this time, you know, we go from the basic rectangular coordinate equations, which, you know, x comma y type equations, into polar equations. So what is a polar equation? It's the same thing as before, as what defines an equation, right? It's variables separated by an equal sign, but always we're going to try to write r in terms of theta. So everything that has theta is going to be on one side, and we want to isolate the r by itself. So this equation, r equals 5 divided by cosine theta plus sine theta, is a polar equation. Same with this other example where we have r is equals to 3 times cosecant of theta. So those are two examples of what a polar equation looks like. Okay, so let's do a couple exercises transforming or converting an equation into polar. So the directions are, and they'll always be, to express r in terms of theta. So we need to remember those previous definitions. So I'll write them here on the side. X is equals to r cosine of theta, y is equals to r sine of theta. That's what's going to help us here, right? So here's x, here's y, here's y. So r cosine theta plus r sine theta equals 12. Now I want the r by itself. So notice how both terms have an r. That means I can factor it out. So if I factor out an r, this becomes cosine theta plus sine theta equals 12. But then I still want r by itself, so I'm going to divide both sides by cosine sine. So r is equals to 12 divided by cosine theta plus sine theta. And I'll be done, because now r is all by itself. There is no x and y's left over, and it's all in terms of theta. Okay, so hopefully that makes some sense. Now let's work on problem B. So this one's going to be a little bit more intricate. Again, I'm going to write out the two definitions that we'll use. X is equals to r times cosine theta, and y is equals to r sine theta for sure. Now we're going to replace those values in, right? So this is r cosine theta minus 1 all squared plus r sine theta all squared equals 1. Okay, now don't be quick to bring in that square in like this, like that's not correct. The problem why it's not correct is because it has that minus 1, right? Or that's two terms, right? It's a binomial, so that's why you cannot do this. So what do we have to do? Well, we got to do the following: r cosine theta minus 1 times r cosine theta minus 1. Now in this second expression, the r sine theta, that is where you could actually just say r squared cosine square of theta, because it's one thing. It's r sine theta times r sine theta. So it becomes r squared cosine square. Oops. No, that should be sine. Sine square of theta. And all of that is equals to 1. Okay? And the reason why I said this problem would be more intricate or a little harder is because we have to FOIL this. And that is not conventional. We're not very, at least we're not very used to doing this, other than having x plus a number there, right? So let's do it very slowly. So r cosine theta times r cosine theta is r squared cosine square. Then r cosine theta times -1, it's minus r cosine theta, and then -1 times this is where I'm at next. It's the same thing, negative r cosine theta, and then -1 times -1 just becomes plus 1, right? And then plus r squared sine square of theta equals 1. So hopefully that makes some sense as to what I've done so far, right? This is the F, this is the O, this is the I, and this is the L in FOIL. Okay? Then I'm going to combine like terms. So r squared cosine square of theta minus, I have two of the same, so 2r cosine theta plus 1 plus r squared sine square of theta. And if you have lost the point of this, remember the point of this is to have r by itself and everything else in terms of theta, right? So we want to solve for r. So a couple things that we can do is notice this 1 here. I'm going to subtract that 1 to the other side to kind of make things less crowded. So I have r squared cosine square of theta plus, I'm going to move the r squared sine theta closer to the other. Notice how everything has an r. And at least these two right here, this are going to be important. So r squared, factor it out, cosine square theta plus sine square of theta minus 2r cosine theta equals 0. Well, this right here is one of the Pythagorean identities. So this is just a 1, so we're left with r squared minus 2r cosine theta equals 0. I still have an r here and an r there. That means I can factor it out. So if I do that, I have r minus 2 cosine theta equals to 0. And it's going to split up into two things by that zero product property. So I'm going to change a couple colors so that you know what's going on. So r equals 0 is one of them. And then r minus 2 cosine theta equals 0 is the other. So r equals 2 cosine 0. Okay? Since r equals 0 is just a single point, right? Having radius 0, it's at the very center of the origin. We're not going to include it into the solution, but this right here is an equation. Okay, so I guess we can say the polar equation for what we started with is going to be this right here. Okay, so hopefully that made some sense. It was quite a good exercise. And if you don't understand something, just go back through the steps. Next, we're going to do the opposite. We want to go from converting an equation that is in polar form to something that is in rectangular form. So there are 4 definitions that we want to use or keep in mind at all times, right? And it's these 4 definitions here. R squared is equals to x squared plus y squared. The definition for x, which is r cosine theta. The definition for y, which is r sine theta. And kind of the definition for theta. We need to take tangent inverse of both sides or just use the reference angle idea. And remember that it is y over x. Okay? And the goal is to have the equation with the variables x and y, right? That's the whole point, is to try to rewrite it in terms of its main variables. Okay? These examples, let's go ahead and do them. So if we are converting the radius equals 5 into a rectangular equation, then how do we do it? Based on, let's bring in those definitions from above so that we can see them and potentially use them. Okay, so let's see if we can make use of them. Now, this one has an r equals 5, and that has an r, this has an r, and you say, well, do I just plug it in, and does that give me an equation in terms of here's x or here's y? No, the problem is that you would need a theta as well, right? And we are not given a theta, at least in example A. So what we want to do is fit it to the first equation here. So how do we do that? Well, we do that by just making use of some algebra. So I could try to get this definition equals to r by itself, but it's better if I just square both sides. And now I have r squared equals to 25, and that's kind of what I need from there. So 25 is equals to x squared plus y squared. And if you try to graph this, this gives you a circle at the origin with center at the origin with a radius of 5. And that's it. That would be the rectangular equation for question or part A. Then let's do problem B, which we're given theta equals to pi over 4. So same problem as before. Which one do I pick? How do I do this? Do I just plug it into this equation and solve for x or solve for y? Well, the problem is that you're not given the radius. So you would be missing a variable for those two, and this definition doesn't have theta, so we're left with using this. So tangent at pi over 4 equals to y over x. Well, what is tangent at pi over 4? That comes out to be a 1. And this is not really an equation that we're kind of used to seeing, so we're going to multiply the x to the other side and have y equals x. And that is something better. We've seen that before, and that is just it's a linear equation with slope 1 and intercept at 0, right? Y-intercept at 0. So perfect. That works. What about C? The radius, or r, is equals to 3 cosecant theta. So how would we do that example? First, rewrite it in terms of sine and cosine, right? That's going to be the best thing to do. So r is equal to 3 over sine of theta, right? That makes it a little bit more obvious. Well, I hope that it makes it a bit more obvious that I can multiply that sine theta to the other side, and it becomes sine r sine theta equals 3. And what is r sine theta from our definitions? Well, that is equals to y. So y equals 3 would be the definition or the equation in rectangular form. And the last one you may already know, where we're going with this. So let's see, what can we do for this? Definitely not like the problem C, where we multiply to the other side to gonna get it easier. This one's a little harder. So what can we do? Well, kind of get creative. So what we can do is multiply both sides by r to kind of get some things going. Now we have an r square on the left and r cosine on the right. So if we replace that with x and y, let me get some room here. Okay, so r squared is what? X squared plus y squared equals 2. R cosine theta is equals to x, so negative 6x, right? So I can move this to the left side, so I have x squared plus 6x plus y squared equals to 0. So you may or may not know this, and the next step will be to get this to resemble the equation of a circle. So what we need to do is complete the square. So we want to be able to factor this perfectly, and there is something missing here. And we do that by dividing this number by 2 and then squaring it. So 6 divided by 2 is 3, and then we square it to get 9. So that is going to be the completion of the square. So but then whatever we add on the left, we have to add it on the right, just so that it is balanced, right? Can't change the balance of the equation. And then the point of all that is that this right here, well, I guess this right here now can be factored perfectly into x plus 3 squared plus y squared equals 9. And so now we're done. This is the best solution that we could use. And if you don't remember this, well, here, let's see, this would be the equation for a circle in rectangular coordinates, where h and k are going to be the center of the circle, and then r is the radius. So negative 3 comma 0 is the center of the circle with radius 3. So this is the template that we were trying to go for, and so somehow we got that equation, and it's in terms of x and y. And that completes the lesson 6.3 about polar coordinates.